Let us discuss here the differentiation of complex functions. By complex function, I mean a function that is defined on some interval AB and takes complex values as an output. When we look at the complex function, they have the form f of t equals f1 of t plus I f2 of t, where f1, f2 are both real functions. Okay, they go from AB to the reals. Okay, here, of course, I mean t between A and B. Now, when we take the derivative is defined the way we would expect. F prime of t is the limit as h tends to 0, f of t plus h minus f of t divided by h. And here, when we write it as a sum of the real and imaginary part, we have f1 t plus 8 plus I f2 t plus 8 minus f1t minus I f2t divided by 8, and then it's clear we can group terms, the f1s with the f1s, because those are the real parts, and then the imaginary parts. So let me just copy paste here. Okay, we have the real part and the imaginary part. So this would be the f1s, this would be the f2s, oops. And then here we have a minus I. Okay. A plus I, sorry. Now it works. And then it's clear that this is f1 prime of t plus I f2 prime of t, which is what one would expect. Okay, so we are just taking the derivatives of the real and imaginary parts. Now, lots of things we have seen still work in this context. Okay, the rules for the product, all those things still work. But for example, the mean value theorem of L'Hopital no longer work. Okay, this is important to keep in mind because, well, obviously, right? Okay, so let me show you an example why they don't work. A counter example. Okay, so the mean value theorem doesn't work for complex functions. All right. The counterexample in this case is f of x, the exponential of ix, which is by Euler's formula, cosine of x plus I sine of x. This is sometimes taken as the definition of the complex exponential. Okay, depends on the book you are reading. Now, when we look at this function, which is of the type we have seen, okay, this is what I was saying. This is the definition, this identity of the complex exponential. But if you look at it only the right-hand side, it's the type we were discussing. Is f1 of x, f2 of x, okay? Now, what we want to check is if fb minus fa equals f prime of c b minus a for some c in the interval ab. Okay, so this is what we don't know. Well, I said already it's not true, but we don't know. And we need to figure out if it holds or not. So let's pick b equal to pi, a equals 0. Okay, so that we are working on 0 to pi. Okay, here, well, I mean, this is clear, right? Because is where the function is working. X is an angle, and it's producing all the numbers in the complex unitary circle. Okay, so for every x, it's producing cosine of x plus I sine of x. So f of 2 pi minus f of 0. Let's compute this, and then we take care of the derivative. So this is clear. Okay, this is cosine of 2 pi plus I sine of 2 pi, which is 0. Okay, plus, minus cosine of 0 minus I sine of 0. Okay, and this cosine of 2 pi is 1, cosine of 0 is 1, so 1 minus 1 makes 0. Okay, so nothing to do there. The derivative, okay, here we can just compute it from the exponential. Okay, it will have taken the complex variables course. We know that this, we can do the derivative as we usually do. Okay, so it's the exponential itself times the derivative of the numerator. But if we are not very sure, we can still take the derivative. Let me do it here. The derivative of the cosine and the sine, so that the derivative of the cosine is negative sine of x plus I cosine of x, which is I times cosine of x plus I sine of x, right? Because when I multiply, I squared makes the negative 1. And this here is the exponential of ix. Okay, so it's clear. Now, the modulus of f prime x for any x, I said it here already. I said the points of the exponential were in the unit circle. Okay, that's clear because it's cosine of x plus I sine of x, the Pythagorean theorem. Okay, but if we look at the product of the two modules, this is 1. And here we run into a bit of a problem because for this to be true, well, it's clear already that it's impossible, right? This would be 2 pi 0. We will have c, and here we will have 2 pi. Okay, taking modules on both sides. This is 2 pi times 1, but this is 0. So no chance. Okay, and that completes the example. So it cannot hold. And the second example that I wanted to show is that L'Hospital rule does not work for a function from AB to the complex function. There we go. In this case, the counterexample that we will be looking at, let's call it G. Well, if you remember the way the hospital was stated, it was like this: when x tends to something, let's say, well, x0, the derivative of the quotient of the two functions was equal to the quotient of the derivatives. Okay, so the limit of the quotient of the functions equals the limit of the quotient of the derivatives. And this was in certain cases, right? So 0 over 0, infinity over infinity, and so on. Okay, the way it's written in the book is a little more general than what we usually see in a calculus course. So let's find f and g. So we are going to take f. One of the two we can just take it easy. So we take the identity f of x equals x. On the other one, we are going to take x plus x squared exponential of I over x squared. Okay, so when we look at these two, let's say we want to compute the limit as x tends to 0 of f of x over g of x. Okay, so this would be the limit x to 0, x divided by x plus x squared exponential of I over x squared. So I can do some cancellation here. 1 over 1 plus x exponential of I x squared. And the only question now that we need to be careful is what happens with this exponential here. But nothing to worry about, because we have just discussed that this has modulus 1, because it's the cosine of 1 over x squared plus I sine of 1 over x squared. So it's going to be always on the unit circle. And the thing is, as x tends to 0, 1 over x tends to infinity. And this is going to be turning around over and over and over, okay? But because it's multiplied by x, as it turns around, it will also sink towards 0, okay? So it will do a spiral and eventually go to 0. So the limit here, okay, is equal to 1. Okay, because the denominator goes to 1. So yeah, we have half of what we need. Now we need to compute the limit as x tends to 0 of the derivatives. The quotient of the derivatives. So let's get to it. Here, of course, f prime is 1, nothing to do there, but for g, which is x plus x squared and so on, this is 1 plus 2x exponential of I over x squared plus x squared exponential of I over x squared times the derivative of the numerator, which is 2I divided by 2 x to the power 3 with a minus. There we go. Okay, so when I simplify, these two go, okay, this becomes 1 plus 2x minus 2I over x times the exponential of I over x squared. Let's see, 2x minus 2I over x. Yes, that's it. Okay, and here we are going to be working, let's say 0 less than x less than 1. Okay, I don't think I said this before, but we are going to be working on the segment. I didn't say it. So let's say it now, on 0, 1. All right. Yeah, so what is the limit as x tends to 0 here? So here we need to look at the quotient f prime of x divided by g prime of x, which is 1 divided by 1 plus 2x minus 2I over x exponential of I over x squared. And I don't know you, but I don't see very clearly what is the limit in this case. Okay, so the limit as x tends to 0. So we are going to do a little estimate here. Okay, usually when you have complex stuff, it's always easier to work with the absolute value, the modulus. Okay. So that's something that we can try first. If that doesn't work, we try something else. But I tell you already, it's going to work. Okay, so let's see what estimate we can do here. Let's actually work on the denominator separately. Okay, we'll have the modulus there. And here, because I know already that the modulus, the absolute value is positive, the modulus, okay. I'm going to try and make a sandwich here. Maybe that's not the most technical way to say it, but I'm going to do an estimate from above by something that goes to 0. In that way, I will be able to show that the limit is 0 and I'll be done. Okay, so that's my goal. But if I want some estimate from above, then I need to estimate the denominator from below. So I need bigger or equal than something. And the prototype inequality, when you have a modulus and you want to estimate from below, is to estimate by the difference, right, of the modulus of one of them in absolute value in modulus minus the modulus of the other. Okay, but one is positive, so that's it. Okay, that's one of the inequalities we learned earlier in the semester. So let's say a minus b bigger or equal than the absolute value of the difference of absolute values of a and b. So that's what we are using here. Yeah, so that's good for us because then this is 2x minus 2I over x times the modulus of this exponential, which is equal to 1. Okay, so that will not bother us. And then we just need to work on this part over here, but we can factor 2x, pull it out, times 1 minus, wait, nope. So this is 2x squared minus 2I. No, that's not what I wanted to do. Sorry about that. So this is 2x squared minus 2I divided by x. Let's write the whole thing. How will this look better? Let's move it over here. There we go. There we go. Sorry about that. Okay, so this is 2 divided by the modulus of x times 2x squared minus 2i. And the 2's are already out, so these have to go. All right. Because x is in 0, 1, actually I can remove the absolute value. And then the only thing that is left is, what is this absolute value here of x squared minus I? And we need to see that in the complex plane. This is I here. So this is 1. And x squared is going to be somewhere in this interval. Okay. But if we look at all these distances, here, 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 we see that the shortest is precisely this distance here, which is 1. Okay, so this is bigger or equal than 2 over x times 1. Okay, so that's all we need. So now this is, bigger or equal than, let's continue here, 2 over x minus 1. And here notice, it could be 2 over x minus 1 or 1 minus 2 over x, but clearly 2 over x is larger than 1, okay? Because the smallest it can be when x is in 0, 1, the smallest is when x equals 1, which is 2, much larger than 2. So 2 over x minus 1 it is. And that's it, because once we have these, now we remember what we were doing. Okay. Yeah. Let's keep this here. Okay. There we go. And let's continue the computation that we were originally doing. Let's continue it here. So what we were doing is 1 over, and then the estimate of g prime, which we estimated by 2x minus 1 from below, 2 over x minus 1. And that's it, because this is x over 2 minus x. And when x tends to 0, this tends to 0. And here's the sandwich I was saying, because this modulus here is positive, but also is less or equal than something that converges to 0, then I can say confidently that the limit as x tends to 0 of f prime of x over g prime of x equals 0, which is different from 1, which was the limit of f of x over g of x. And that finishes the question.